Hello friends, myself Rahul Chakule. Uh, Now in these presentations we are looking the second problems based on Kliens construction method. So already you know this Kliens construction method comes in unit number 6. Unit number 6 is having the two methods. First, relative velocity and acceleration involving the Coriolis component, and second graphical method is the Kliens construction. So already we have discussed the Kliens construction method in problem 1. Before going to see this another problem, we will summarize the different features of the Kliens construction. Uh, this method is only applicable for IC engine mechanism. Okay, so this method is not applicable for four bar mechanism or the mechanism having more than four links. The second feature I would like to say, this method is very simple and less time consuming. And third is that in relative velocity and acceleration method, we have drawn the velocity polygon, acceleration polygon separately. But here, both the polygons you can make on the same given slider crank mechanism. So because of that, it is simple and less time consuming. This process of construction is given by Kliens. So based on so that's why the name of this method is the Kliens construction method. Um, there are some formulae which is applicable to solve the unknown by the Kliens construction method that we have summarized earlier. Now in problem number 1 we have seen that problem was based on case number 1 where the crank is rotating with uniform angular velocity. Now in this validation or in this discussion, we are going to see the another problem where the crank is rotating with non-uniform angular velocity. So let us take the problem 2. Here it is by mistake it is mentioned case number 1, but it is the case number 2. The crank is rotating with non-uniform angular velocity. So in the problem IC engine mechanism, the crank is rotating at 250 rpm in clockwise direction. The length of crank is 0.15 meter. The length of connecting rod is 0.75 meter long. When the crank turns through 40 degree from IDC and when the angular acceleration is 100 rad per second square, it is the problem is asking the unknown, that is the acceleration of slider. Okay, so only one unknown is there, that is the acceleration of piston. Now how to solve this problem for getting the unknown? Again, the different steps are discussed by the Kliens. The name is given as Kliens construction. Some types of construction has been given by the Kliens. So the same one, only some changes are there. First of all, you draw the configuration diagram by using the scale. Here again the dimensions are in meter. So I have chosen the scale for configuration diagram as 1 centimeter is equal to 0.1 meter. Then a second main task is to make the Kliens velocity and acceleration polygon. Again, the method of velocity polygon is same. You draw the perpendicular line from O This perpendicular line from O is perpendicular to the line of action of the slider. You draw this perpendicular line. You extend this connecting rod CP line, and where this perpendicular line and connecting rod line is intersecting, you give the notation as capital M. So this triangle OCM is the velocity polygon, right? Now, how to make the acceleration polygon? First of all, you draw the two circle, one small circle, center C, and radius CM. Okay, center C and CM as the radius. You draw the small circle. Then you draw another big circle as CP as the diameter. So you take the CP as the diameter. You draw the another big circle, and these two circles are intersecting at top side at K and on the bottom side at L. So this is up to this one it is same, but here the crank is rotating with non-uniform angular velocity. So when there is a non-uniform angular velocity, means the velocity of the crank is vary, means the acceleration comes into picture, and that's why in the problem the value of angular acceleration is given 100 rad per second square. Means this problem is based on case number 2, where the crank is rotating with non-uniform angular velocity. Okay, now when the crank is rotating with non-uniform angular velocity, there are some changes in the construction. Okay, the changes is that you draw the line O1. Okay, and this O1 is having a magnitude as well as direction, because it is the tangential component of crank. The crank OC is there, that is a normal component of acceleration, and because of the alpha value for crank, the another tangential component is there coming into picture, and that tangential component is always perpendicular to the normal component of crank. So it's clear, and this tangential component is perpendicular to normal component, so you know the direction. Now what is the magnitude of O1? So for getting this magnitude of O1, we have two formulae. Number one is the tangential component of crank is equal to this OC into alpha. That this formula we have used in the relative velocity and acceleration method. That is the tangential component of crank is equal to length of crank into alpha of the crank. This is one formula, and the second formula is the formula given by this Kliens construction. That is the tangential component of crank CO is equal to OO1, that is length, into omega square. So if you compare this LHS, it is same. So we are going to equate this right side, where omega you know, alpha it is given, the length of OC is given. So from this O1 is you can determine, and this O1 is equal to 0.0218 meter. Okay, so you take accordingly 0.0218 meter as per the scale. You take in the centimeter length. So this O1 is the this value 0.0218 divided by 0.1, that is that much centimeter. You take that centimeter length as O1. Okay, so this is a somewhat changes because of non-uniform angular velocity of crank. So from that O1, you draw the uh, parallel line to the line of stroke of the slider, and this parallel line passing through the O1, it is intersecting at the line KL. Okay, so when you draw the line, when you draw the line from O1 parallel to line of action of the slider, this line is intersecting to the line KL at N1 position. So N1 is the position of intersecting this parallel line drawing from O1. It is intersecting to the KL line, and in this way, this particular quadrilateral O1 C Q N1, O1 C Q N1 is the quadrilateral, and this quadrilateral I will say it's a acceleration polygon, right? And after getting this velocity and acceleration polygon on the given mechanism by the method or by the constructions suggested by the Kliens, the unknown in the problem is to find the acceleration of the piston. So again we have the formula AP, that is acceleration of the slider P, is equal to O1 N1 into omega square. So O1 N1, you measure the length O1 N1, you multiply by scale, and then you multiply by omega square. The O1 N1 comes 0.15, that is a O1 N1, you measure the length, you multiply by scale, that comes 0.15 meter, and you multiply by omega square, the final answer comes 102.8 meter per second. So in this way, you have to solve the problem where the crank is rotating with non-uniform angular velocity. Almost I will say the 90% method or constructions is same as we have done for case number 1. Only changes is O1, that is a tangential component of crank. It somewhat changes in the formula because of this O1. So I will say it's over. Thank you.